and they're connected into this 74-279, which is I think it's a quad flip-flop. 279 RS flip-flop. I didn't write down how many stages, so give me a second. Try not to burn my hand on the soldering iron. So 279, and it is, yep, a quad RS flip-flop. Now, why did they use this versus another 273? Don't know. First guess would be they didn't need all the gates, so they just picked a smaller and maybe cheaper part to do it. But before we get ahead of ourselves here, I want to check all these interconnects. So these four here are connected together. Which are then, yeah, do the 220. Not that one. Not that one. Yep. So these four here, 1, 2, 3, 4, are connected to that transistor. So let's go for the next one. Yep. Seven. Those 7 there are connected to that transistor. So these 8 here are hooked to this transistor. So this circuit here can all go away. And I said these 7 here, I should have counted this one too. So yes, it's these 8, and these 4. So we've proven to, or I've proven to myself here, that these 3 transistors only drive this little section here, and I don't have a use for them, so they can go away. Now, I assume they hook to this chip. Here you can see this connection going in underneath, but you can't see where it comes out. And that's a decoupling capacitor. So now let's go on the back side. The center one of each group of 3. So these 2 here go to pin 2, 3, 4, 5, 6, 7, 8, 9. So pin 9 better be an output, otherwise I'm completely off base. Yep, pin 9 is an output. So that matches up. 10, 11, 12, 13 is an output. Yep, that matches up. So 1, 2, 3, 4, 5, 6. Where's 6? Pin 6. As an input to 1. So I want 4, 7, and 9. 1, 2, 3, 4. 4 is not on this side, and 4 is not shown on this side, so I'm going to have to pull that off. Well, no I don't. Let's say I was going to have to pull it off before I can see where it goes, but I can always beep it out. So, okay, 4 goes there. 5, 6, 7. I have a guess. Nope, 7 does not go there. Let's see a connection on this side. Now this is a set reset flip-flop, so this is a little different than the octal Ds. Here you can see the truth table. Basically, when you poke set, it latches it on. When you poke reset, it latches it off. Otherwise, when they're both high, it keeps the last value. So there's really no data strobe to this. It's either you turn it on or turn it off. It's sort of like a latching relay. You poke it once, it stays there until you poke it again to turn it off. So a bunch of these pins are going to have to go back somewhere. And looking at this, that somewhere is the chip right above it, which is a 138 3 to 7 or 3 to 8 decoder. Now, the real question is there anything else? There's one more flip-flop right there, which I don't see wired to anything, but there could be wires underneath that are hooked up and it goes and drives something else on the card that may be important. I always run the risk of damaging the part or the pad when I desolder pieces off the card. So I typically like to be pretty sure that I don't need a connection before I pull it off. So I'm just going to poke through this real quick. See, I see this trace right here. Oops, sorry. Oh, it comes off a different 138. Oh. Okay, pin 7, which is the output, is heading back to somewhere over here. Pins, yeah, 7. So it looks like this flip-flop is used somewhere else in the circuit. So I don't think I want to pull him off at this time, which is kind of unfortunate because it would have, just cleaned up a little bit more of this area and less things to worry about. So I think for right now I'm going to nuke the transistors and these resistors and leave these guys until I know more about the rest of the circuit. So we'll start with the transistors. Again, I'm keeping the parts in case I need spares to repair stuff. And then once the sign's fully up and operational, I may throw some in a little ESD bag and pack it in the back of the sign just as spare parts if I find any dead ones in the repair process. That's typically an indication that it's a common problem and it'll show up again. And if I don't find anything, or I have lots of left or lots of the same value, the extra ones just go into my grand parts supply and typically get recycled into other projects or repair other stuff. I mean, just because it's 31 years old doesn't mean the parts are no good anymore. Like I said, a lot of the 74,000 series parts are still purchasable today, and a lot from the same manufacturers. Numerous ones of the parts on this card were made by Texas Instruments, who still makes all the same parts. Now, over time, the specs have probably improved, so the part you buy today, before it might have been like the top end of the bin. When I say binning, when they make parts, especially silicon parts, a lot of times they make the part and they're not exactly sure how fast it can go or how much current it will draw. So after they make the wafer, they put it on a tester that then will run that chip through a series of tests to figure out A, how fast can it switch, and B, how much current it will draw. From those readings, they then put the part in one of many bins, saying, oh, this part's fast enough and its current draw is low enough to be an LS part, or oh, this part draws more current but it's faster, so therefore it's an S part. Well, as silicon technology gets better, those bins are easy. The higher speed bins are easier to fill. In other words, more of the silicon can be a top end chip, versus where before they may have only gotten a few parts that made the top end bin. So when that happens, they don't just discontinue the old parts, the slower, more current hungry parts. They just take some of the premium parts and down bin them. Exact same part, exact same everything. They just mark it as something inferior with either a slower speed grade or a higher current draw, even though it doesn't really need that. This is really common today in processors. So your 2.5 gigahertz processor might have actually been a 3 gigahertz processor, but Intel didn't have orders for 3 gigahertz, but they had orders for 2. So they just took a 3 gigahertz processor and marked it as a 2 and shipped it out the door. Because it'll work perfectly fine as a 2, it's just you're not using all the capacity that the silicon, or all the performance the silicon had to offer. And that's what a lot of your overclocking crew banks on, is they're like, hey, Intel tests these higher, or bins some of these parts higher than what they're actually selling them at. So if I sit there and tweak my system, I might be able to get X% more performance out of the same part without paying the premium for a part that's guaranteed to go that fast. Okay, next up, I think I'm going to take out the pen input connection. Mostly just because it's a connector with little wires in the back and it's in the way. As I do this, I'll try and explain it and hope my battery on my camera doesn't die. It's about that time. Probably should just go change batteries so I don't have to worry about it. But let me get started on this. So this is just a little sort of headphone type jack. Although it's kind of interesting that the knob is loose in it. Just on 2 little wire stalks here. So this plane here, I'm willing to bet is either power or ground. Well, it's marked ground, so we'll go with ground. So I can just solder suck the ground out. Maybe. Again, there's a lot of copper and solder on that connection, so it's hard to take out. And let's take out the pen input. So there's the pen input jack. 2 wires. So whatever, either CDS cell, photodiode, whatever, wasn't active. So the pen was just like a passive part on the end, maybe a transistor behind it, and then ran back to the pen input. Now I say passive, but it could have been semi-active. If the sensor was like a photocell with a transistor behind it, that would have boosted the draw up. Now, if you look at that input, it goes over to a transistor and a pull-up. No, it's a transistor and a pull-down. So this connection in here goes to this resistor, which then is in the same ground plane. Even though that said ground for the pen input, I want to beep it out real quick and make sure that it's actually ground and not some other signal. Nope, it's really ground. So I'm betting the pen input is either a photodiode or solar cell, because the way this transistor is set up, there's no other connection to that pin. Oh, that doesn't, that's the emitter. This is a really odd little circuit. Maybe I have to draw this one out. And there is no other connection to that. So I'm just going to use the back of the sheet of paper, since this isn't a core thing, and draw out how this circuit was. So you had your pen input here. And it comes in and hits the emitter of this transistor, which is really quite odd. I mean, I would not have guessed that arrangement. And this is the same 222 NPN transistor that we've seen before. Now there's also red, red, yellow, so that'd be 3 zeros, so 22K? No, 220K. There's also a 220 kilo ohm resistor to ground. So whatever this pen input was, it must have been active. I mean, there was no power supplied from the card, I don't think. Hold on. Nope. That outer ring is not connected to anything. And there was no power from this card going up this pen connector. It had ground on one side and this little weird input circuit on the other pulling it down. Now, maybe this was some sort of input gate so that, you know, the circuitry over here could shut down the pen input to keep noise out. I'm not really sure yet. So anyways, let's start following it through. So the collector side of the transistor, yellow, purple, orange, 47K, yellow, purple, yeah. Nice, no other connection at the top. That goes over to that guy, who then hits, you know, the 5 volt trace. At least I'm pretty sure that's 5 volts. At that point, and beep. Yep, so that's goes to 5 volts. So, you know, I'm just sort of at a loss here as to how you get an input from this. I mean, this looks like an output port. Unless there's a trace here, I just can't see coming off of that, but boy, I mean, it's pretty straightforward. Now let's keep tracing it through and see what happens.